All right, welcome to the first lesson on Unit 10 for continuity and limits is our whole Unit 10. So this lesson we're just going to focus on limits. So as we get through our notes, we start with just some general concepts, starting with the fact that limits are the fundamental study of calculus. It's actually, they don't really call them limits in calculus, but that's really what they are. They refer to them as derivatives or integrals, depending on how you're looking at it. So as we get through that, we want to note a couple things. The first thing is the limit. In order for the limit to exist, that doesn't mean that if you plug in a particular x value, just because you don't get an answer, it doesn't mean the limit doesn't exist. It just means that there's no function value there. So what we've talked about so far already in this lesson is that you might have a hole in your graph, but you can still have a limit, because the limit is the idea that we're asking, if we were to look just before and just after the x value being asked about, where would we think we would go? Remember the example introduction with the TV screen and the buffering. We didn't care what happened at exactly 4 minutes in the soccer game. We were able to kind of estimate what would have happened at 4 minutes based on 3 minutes 59 seconds and 4 minutes and 1 second. So that's really what this please note box is saying, is that just because we didn't see the 4-minute mark in the video doesn't mean that that moment in time didn't happen. Okay, so we can also look at this notation. I think at this point we have a pretty good handle on it, but it is asking the limit, LAM, the limit of a function as x is approaching this number. So in this case 3. We eventually got down to what is happening, what is the limit as x, or in this case a, gets really, really big. We can see this thing tapering to a certain value, then we can have a limit existing for infinity. There we go. So when we start looking at limits, the first thing we learned was that we can just use direct substitution. So given this function x cubed, it's going to be one of those, like it kind of goes up and over and up again, something like that. But anyways, we're asking, what is the limit as x approaches 2? So what that's saying is, let's go to the graph at x equals 2, and that looks like this. So here's my graph, x cubed, x squared, and all that. Okay, it's asking, what is the limit as it approaches 2? In other words, it's saying, not necessarily that I care that 2 is defined. Okay, if I can get it to exactly 2. There it is. Okay, so it does exist. 2, 4 does exist. But the question's not directly asking that, but let's do this. What happens as we approach it from the left? As the graph is approaching from 1 to 2, where would we expect to land? So, I mean, in a really rough way, I'm just dragging this along. As I'm getting closer to where would I expect to go, well, I'm seeing my numbers heading to 4. Same thing over here. As I'm approaching 2 from the right, so I'm going from 3 down to 2, I'm seeing my numbers also getting close to 4. So without actually seeing what the value of plugging 2 in, I would expect it to be 4. The nice thing is, in a direct substitution, if you can just plug it in, so 2 cubed minus 2 squared plus 2 minus 2, if that exists, then we know that the limit is exactly whatever we plugged in to be. So, let me get my pen going here. Where's that going? And in doing so, we say that the limit as x is approaching 2 is equal to 4. 2 cubed is 8. 8 minus 2 squared. So 8 minus 4, that's 4. 4 plus 2 is 6. 6 minus 2 is 4. Okay, So the first thing you can do is directly substitute. If you get an answer, you can be done. If you plug it in and you get like a 0 in the denominator, then we have to try something else. Okay, but graphic is solve using graph and trace. Well, that's kind of what I just did. I was proving it other ways, but that's one way to do it. Using a table, I'll make that a separate video actually, because I want to keep going in the content of limits here. So again, we can try it and it works great. Direct substitution again here. Evaluate the limit as x approaches 3. Direct substitution says we can directly substitute 3 in for x, and I get 2 times 3 squared over 3 plus 1. 18 over 4, which equals 9 halves. Okay. Well, I'm going to pause for a second, get that in the graph, and I will confirm that graphically, but again, direct substitution shows that we should be right around 4 1/2. Okay, so we head back over to the graph. There's our function. I'm going to estimate graphically. I'm going to get up to 3.5. No, not 3.5. Sorry, we're trying to get to 3. There we go. If I get to 3, I see that my value was 4 1/2. So I can confirm graphically, or I can substitute directly. But either way, it works. So just more examples of that. I do want to keep going, get this to work in one video. So side note, the difference between a hole in a graph and vertical is a vertical asymptote is produced when you have, you can look at the notes to get all the written out parts, but if I factor out x squared minus x minus 6, what I get is x minus 3 and x plus 2. Right, so that's factor it, x squared plus 2x minus 3x gets us minus x, and then minus 6. So what we get on top, if we factor it, we get that, and then we get x minus 3. That's from this guy here. An asymptote is produced if this denominator did not have a matching factor in the numerator. So what this one here gives us, because we have x minus 3 in top and bottom, this is actually a whole. If we were to look at this function here, I'm going to bring that down to here, we get x minus 3, x plus 2. But instead we get x plus 3 on the bottom. Now this denominator, x plus 3, does not cancel. So what this means is when this equals 0, so at negative 3, we get an asymptote. Up here, x minus 3 cancels x minus 3. So what we get is at x equals 3, the thing that makes this 0, we get a whole. So the way you check it is, if the denominator factor cancels with something in the top, you solve that factor for 0, and at that point, you get a whole. So at 3, we get a whole. Here, if the factor does not cancel with something in the numerator, what you get is solve the denominator for 0, so x is negative 3, but at negative 3, we have an asymptote. Okay. I think I'm gonna I might be able. I want to keep these videos a little bit short. I'll probably just work through some algebraic examples in a second video.